First, I want to just acknowledge some of these folks in this picture here with me: Kevin McGuigan, Kate Collins, Candace McDonald, and Nathan Kroll. My job is, I quite like it, especially being able to work with all these clever young people. And then we've had quite a few contributions from other folks that I'll be talking about, showing some of the stuff they've done today. And I'm really going to talk about this shallow water Topo-bathymetric LIDAR that we acquired about a year and a half ago. Very quickly, the sensor that we're using is equipped with a near-infrared laser, which is what's used traditionally in topo LIDAR mapping, as well as a green laser. The idea being that the near-infrared laser will reflect or be absorbed, but often will give some reflection off the water surface, whereas the green laser will go through the water column and reflect off the seabed and come back to the aircraft. It's real important to be able to map the water surface because the speed of light changes there, and there's a refraction angle change that takes place. So whenever we're talking about Topo-bathymetric LIDAR, being able to nail the water surface is critical. And this would be a typical waveform from the green laser. We have a large backscatter from the water surface. It's a bit of a volume scatter there. It's not just on the top. It can go down up to 1 meter, so it's a little ambiguous for the water surface. We go through the water column, and then ideally we get a back reflection from the seabed itself. Our scanner is kind of unique in that it scans in an elliptical pattern, so we're scanning 14 degrees ahead and 14 back and 20 side to side. And as Jennifer mentioned in her talk, we're flying at about 400 meter altitude as well. This is kind of unique in that it allows us to survey a target twice. So shadowing, breaking waves, things like that, we have a chance to get a second shot in. Last year we flew the first mission with this sensor. We teamed up with Leading Edge Geomatics out of Fredericton for the aircraft support and did the calibration out of Fredericton, and then flew these areas along the coast for a variety of applications. And I'll take you through a few of them today. Quite quickly. Jennifer mentioned water clarity is the big limiting factor with how far that green laser light will penetrate through the water column. These are Secchi disk pictures, and basically our sensor is rated to go whatever the Secchi depth is, 1.5 times that depth. And basically it's a high-tech approach where we lower it down until we can't see it anymore, and that's the depth of water we call the Secchi depth. Not a bad day to fly LIDAR, a very poor day to fly LIDAR. So these are some extra challenges that the topographic LIDAR folks don't have to worry about. It can be blowing and raining, and then the next day if it's clear, they could fly LIDAR or air photos depending on the cloud cover. With bathymetric LIDAR, we have to worry about, has the water column settled down? Has the water clarity cleared up? And sometimes that takes a bit of time. So we're doing a lot of work looking at the weather, the wind direction, the exposure of the shoreline. If it's an offshore wind, that may not be a problem for us. If it's an onshore wind at the same velocity, then that typically will be a problem because it'll set up waves, and of course the waves will stir the water column up and we'll have turbidity. I'm going to show you an example here of Cape John, due north of Truro, where we had 2 surveys, and if you look at it, the wind conditions during those surveys, both from the southeast and this quiver plot, look about the same. But we had strong winds leading up to this, some over 40 kilometers an hour, rotating around from the south to the north. And here you'll see the effects that along this, what we're going to do is look at this cross line on our flight. So here it is on the 24th. And you can see fairly turbid brown water. And we can see some waves in here, maybe not as nice as the radar that Dirk showed us, but we can see some wave patterns. On the south side, remember the wind is blowing from the south, so an onshore wind. Offshore wind here, it's not too bad. The next day on the 26th, look how much things have managed to clear up. So in some cases, things can clear quite quickly if given the opportunity. So we flew a test line over these 2 areas, so let's just look at the LIDAR. Well, we always try to be on the water during these flights, and we were out in the water in this one, and it was pretty darn choppy. And we finally were able to text with the aircraft. We don't talk on the phone, but we can get text messages back and forth. So when this flight was aborted, I wasn't that sad, because I meant I could get the hell off the water and get back to dry land, and that ulcer in my stomach would not grow any bigger. Okay, so let's just look at this in a little more detail. I'm just going to show you a cross-section of the two LIDAR data collections over this area. The green point cloud is from the 25th, so you can actually see the waves quite clearly on the surface returns, but you'll notice no green points made it through the water column and to reflect off the seabed, so no penetration. The next day, on the 26th, not surprising, we had good LIDAR penetration out, and we're starting to see some of these big sand bars and sand ripples out here. The difference is a different state of the tide. That's why there's a difference here. And it's always nice when invariant objects, like the roadbed here, for example, line up between two LIDAR flights. Always a good thing. If we look to the north, you'll notice that the two LIDAR flights are basically producing almost the same amount of detail. So over a short period, or a short distance geographically, we have completely different water conditions. So these are some of the challenges with flying bathymetric LIDAR and monitoring the wind and the turbidity conditions and so forth in order to have a successful flight. We basically had good data on both days there. But we wanted to cover the entire area, so we aborted the mission that first day. This has led us to some additional research, wanting to try to build up time series of areas looking at light, how much light is making it through the water column versus things like turbidity measurements, and relating those to weather station information, wind direction. So we want to know, what is that threshold when the wind gets to a certain point of magnitude or a certain duration, when we can predict that it's not a good day to fly versus a good day to fly. So we've got these light sensors moored, and we've also put some, it's maybe tough for you to see, but we've put some vertically on a pole so we could look at the attenuation of the light energy through the water column as the tide changes, and we have a turbidity sensor and a pressure sensor there to measure the sea level as well. So here's an example of the turbidity measurement. So we can see we had a few days where we had that brown water taking place. And these are just some of the other things this probe is measuring: temperature, salinity, etc. One thing I should mention in context to Vlad's talk about multi-beam, where you have to be very cognizant of salinity and temperature that affects the speed of light, or the speed of sound in water. We don't have those constraints with LIDAR. Salinity and temperature, I won't say don't change the speed, but very minor. So we don't have to worry about that too much. Okay, a little bit busy, but let's keep it fairly simple. This is on the land information. So here was a nice sunny day. Here was a day where we had some clouds moving over, and we see it a bit spikier. Here are the underwater returns, and the different colors are the different levels on that light post. The purple is the lowest one down near the seabed, so it's got more water on it all the time. And we can see the effect of how the amount of light getting to the seabed is much reduced during these turbid times. Now we had a turbidity pulse at low tide and at night. Didn't really affect us. The next day, things are pretty well again. So it's not a slam dunk, super easy all the time, but there's definitely relationships here we can learn from, and this is why we're trying to build up a time series to look at when we think we can fly and when it's not a good time to fly, because we don't have good information on near shore turbidity that we can readily access. Duration. A lot of wind in a short period of time versus a little wind over a longer period of time can have the different effects. There's a strong series of wind events, but not that significant a turbidity, and we have a pretty good light return. There's the same magnitude, but over a longer duration, and we can see how that did have an effect. So right now we're going through trying to look at all these various parameters and see if we can come up with some thresholds on not only when is it not good to fly after an event, but how long do we have to wait until we think the water would clear up again? That's probably the more important part. Okay, let's move down the coast to a place called Little Harbor. For those of you, you may know Malmedy Beach is a provincial park right here. There's just one of our first products we make is to look at the flight lines to make sure we don't have any gaps in the data. We fly at 30% side lap, and you can see how everything is a bit wiggly. This is essentially just the attitude of the aircraft during the survey. And we always fly one of these cross lines. With our sensor, I didn't have a graphic here to show you all the components, but we also have a Leica RCD30 camera, so it's true color and an infrared band, so we can do NDVI and look at things like submerged or floating, in this case, aquatic vegetation, so very sensitive to vegetation in the near IR. So that's a really nice complement to the LIDAR is to have that. And at 400 meters, we're at 5 centimeters as well. I think Jennifer used the same resolution. We also have a quality assurance camera that comes with the sensor as well, but it's more like 20 centimeters. Looking at validating the LIDAR, so we're comparing RTK GPS points here, and we're in the 5 centimeter range, plus or minus 4 centimeters. So well within the spec on the Topo. The bathymetric validation is more challenging in these shallow near shore areas. It's challenging to put a boat in there and do multi-beam, for example. So I'll show you some things later on of what we've done to think about that. Jennifer mentioned LIDAR for reflectance, and here's an example of the original flight lines, and this data is not calibrated when it comes off the aircraft. So you can see every individual flight line here. We've then normalized the flight lines so that we've tried to eliminate the seams. And it's a bit ambiguous here because a dark area could represent deep water, or it could represent a deep or a dark target on the seabed, like eelgrass, compared to sand. So the tones, at this stage, you can sort of interpret them perhaps from looking at the texture and so forth and the shapes of the channel, but you cannot just look at a gray value and say, oh, that's sand versus eelgrass because of the loss of the signal in deeper water. The loss is exponential. And of course, looking at the reflectance image versus the air photo, it's a very nice complement. But we don't have all of these patches that you may or may not see here from individual frames being stuck together. That was what I had asked about in your presentation. Of course, here is our bare earth digital elevation model, and here is a digital surface model where we've actually merged the reflectance on top, or in with the data set. So now we're seeing the texture of what's on the seabed as well as the elevation. In this case, we got to about 6 meters depth below our, I guess, zero contour line would be 0 CGDV 28. So this is a very useful and incredibly rich GIS layer to just allow people to look at and see what's on the seabed that I think is even better than the air photo in terms of what you can actually see there. And, when we want to look back at, if we were trying to make decisions about siting aquaculture, shellfish, for example, in this bay, prior to this survey, this would be the most up-to-date information from the old chart. And there's a couple of things I'll just point out. Look how small this sand spit was back in sort of late 40s, I believe. And you see how it has migrated, and this channel is no longer there. Essentially, all of that various storms has pushed sand in and more or less choked off this deeper basin in behind here. So I don't think we've got nearly as much flushing now as we would have at one time. So why we need to get up-to-date information because,